Okay. Yeah, you're working.
And now, on the world's greatest station, we proudly present...
Alright. That's enough. Yeah, they can hear me. Okay. I'm gonna make this quick. Let's find out what I did last stream. Okay. Last stream, LIR, oh yeah, parser 11, so I implemented loop. And before that, I did complete migration to, I talked about this before. Okay, do and break with unreachable blocks. I implemented loop, which means, I think you got to see that as well. I implemented let, and I'll show you how let is being, parsed down into. So we can start with main. Main, nothing to nothing. Main, match on nothing to do, and then let t. And then we're not assigning it. We're just doing let t. Expected new line. Okay. All right. So we have here main. Main takes nothing, returns nothing. Match on nothing. Do let t. Yeah, and then what it does is essentially this go to. Actually, no, okay, it doesn't do anything currently. You see here, pattern 01, pattern 0, %3 is void, which is the what's it called, the value of the do. Because imagine if do doesn't have anything, or well, let t doesn't evaluate to anything. It's just that when do hasn't parsed anything in its body, it implicitly returns a empty tuple. The same as just doing this, and it'll generate the same code, I think. Yeah, the exact same code, %3 and return 3. Okay, and then let's assign something. Well, let's match on nothing. On nothing. Okay, so this is the entry. This is the entry point, and pattern 0. This is the first thing. So you can ignore the above, the entry bar. So this is where you need to put your eyes. Pattern 0. So this is the start where the do block. So %2 is the right hand side, and then here the terminator is go to pattern. Matching on %2, not a tuple of %2 though. Just %2, and then when it matches on nothing, it goes to let next. So it's like I'm using this like it's like I'm desugaring it to a match expression. So let me do a like let's do some like pseudocode. 0 equals this match 0, and then this equals nothing, right? And then if I did like let t, it'll go match t to actually no, it'll be like match empty t equals that. That's essentially what this desugars down to. Basically, the same stuff that we use up here is the goto pattern, this unwrapped match statement for all of the pattern overloads. We're still going to use it here. So we're using it in the let expression. So this is basically being desugared into a match with only one arm. But the thing with match statements in this goto pattern is that they can only have one, well, no, they have to be completely exhaustive. So here, this is completely exhaustive. But if you try to do something like this, let t x y in an array of like something that's obviously fallible, and Rust has a notion of fallible let bindings. I'm gonna do this here. %4, %5, %6, %7. Construct an array literal, and %8. Go to pattern matches on those two, and only then you can go to the next. So I split the control flow using go to pattern. I just split it in two. Actually, you can't see this. Yeah, sorry about that. Okay, so yeah, I basically split the control flow in 2 sections when it hit 2 sections when it hits a let, because let can fail. It doesn't fail at runtime though. If like this seems like it can match, right? But it could also fail, right? Let's say the right hand side is that. So it's basically desugared into this match expression using this goto pattern with a single pattern, and this has to be exhaustive. So if it's not exhaustive, it'll raise an error. Yeah, and that's simple. Like, that's what let bindings get desugared to in this language. Super simple. Yeah, that means let x. Yeah, let x actually does something. I didn't save, that's why. Yeah, matches on. Yeah, because this is the pattern for this, but in here, just does nothing. Okay, what else? So let and bug fixes, I did the table. So symbol table, locations and IR changes, debug printing changes. I haven't done color yet because when I tried it, specific color on the IR, when I tried it, I couldn't get good looking colors. Plus, my color scheme was all messed up. But what I did do was introduce these new lines here, and I feel like it makes things look a lot nicer. You're able to tell. I just followed what LLVM did with printing. Okay. So what else? Yeah, and I did cool merging as well. Cool merging. That's another one. Yeah, and continue. I'll show you cool merging. Cool merging is something pretty important. Okay, we'll start here. Uh, let's just do. Okay, we'll do apply. Apply. It doesn't matter. I'm just gonna write a random type. Apply random type. Apply f of fx equals fx. Simple. Oh, expected function time. So at least I do check that. Function pattern matching with different number of arguments. Okay, so I do match that too. So, okay, I do have to put random types, but they have to be in the right order. Okay, and visit dependent. Okay, I won't run the type checker yet. Okay. All right, so here, so I'm applying. Oh wait, that's not right. Yeah, so I'm applying fx equals f cooled with x. So it's just simple here. F is for x6, and then I'm just calling them f3 and x5 is cool, and then red 7. Simple, but what if I did this? Just a whole bunch of that, right? It merges them all together. F3 x x x x x. but there's a specific optimization I'm making here. It's not particularly an optimization. It's just a thing that they do in construction of the LIR. I can show you. Where is it? Cool merging. Oh yeah, I wrote a ton. So, if the current token of the first expression, if the current line number of the first expression equals the line number of the second expression, they're basically calling each other. So, so don't bloat the IR. Merge call expressions at the left-hand side is already a call expression. The checker will unmerge calls based on type information. Okay. Call merging may happen on different basic block boundaries, which means you need to move the call forward into this one. There is also an issue with order evaluation, which is so obviously left to right. However, an issue is posed when function arguments have side effects, which may affect the previous arguments to a function. This is where forwarding to an L value. Yeah, so this is just some stuff that I was talking about before with order of evaluation and stuff. I made some changes, specifically with spilling mutable L values. It probably wouldn't make much sense to you guys, but essentially mutable values, if I'm using them in a call expression, I spill them to an SSA value, just so the order of evaluation is respected when I'm reordering. Okay, so so this is just some reordering stuff. I uncomment this code, and you can see what happens. Yeah, so when it's uncommented, it just goes %7, and then you're calling, 8, 8, 9 to 9, 10 to 10, 11 to return. That's simple. You'll be able to see that. Yeah, and then when I uncomment it, this is the merging. So checks if it's a call, pops it from the thing, pushes it, and then merges it. Okay, let's run it again. Yeah, now they all get moved together. Now let's say x was a mutable. X was a mutable value. These all have to be spilled to stack. See how they're all spilled here? Compared to before, where they're not spilled at all. Because x can't change between the reordering of the expression. If it changes, it's an error anyway. But if it's a mutable value, it's able to change, which means we have to spill it to the stack as a, not to the stack, spill it as an SSA local, because anywhere between the evaluation of these operands, something could happen. Like, let's say, like, if x else x, right? Just pretend this is some control flow. They all have to be spilled to stack. So these are being spilled to stack. There's some control flow here. The value of 11 is being used in here as well. And these are being spilled to stack. So I strictly evaluate from left to right with call expressions. And I always respect, like if it's in the IR and I try to reorder it, like by merging call expressions, I have to respect the order of evaluation, which means spilling the arguments to the as a local. Yeah, so you can see the evaluation of this argument could very well assign x to be something else. X equals 20. And you can see here. Yeah, if then %10 equals 20, x equals 20, which is %10. Yeah, so just assigning that. Yeah, so yeah, and then this branches to if exit with %11, and that %11 is used in the second operand right here. So that makes sense. It took a while to get that right, but I got it right. Yeah, so that's why. And remove the immutability, and these aren't spilled at all. Simple. I think that's pretty simple. All right, what else? Yeah, so for in this language, continue is rep, break is brk, return is ret. These are all the things that I'm using in this language. So I have ret and rep I implemented, and then break, so brk. They're all in this language. That's the names of them. This is super simple to implement. The continue. It's just like break, but without an operand. Okay. Yeah, that's what I was talking about. Proper spillage to respect or evaluation. So I have not exhaustive. Yeah, I have work. I have stuff still to be committed. So when did I get the return keyword? Talk return. Huh. Okay, I should mention that in the commit message. So let me unstage this and undo the last commit. Alright, and just rename that to basic topological sort on symbols. Plus red expression. Okay, and then this thing. You can do checker. It's I think I name it checker. Checker. Alright, basic entry point. Plus fixes. Okay. Alright, now let me get into what I want to do this stream. So the current parser right now, parser underscore expo, parsing an expression, has feature parity with what I did before using the HIR. So the current parser for the LIR is basically equivalent to the last one with the tree IR. So I'm done with parsing, which means I need to get started with the type checker, which means I need to so you know how I changed the parser to generate LIR? I have to change the checker to check LIR, which it's not an easy task because this isn't an AST. There is no nodes in this language. In this intermediate representation, there's no nodes, so I have to find out which way do I go, and I also have to respect bidirectional type inference, right? I talked about it before, how type information can flow up and then flow down. So I need to make sure that's possible inside the type checker. But there is no nodes. It's like a tree, right? But there is no roots. It's kind of hard to explain, but it's really non-trivial. It's pretty hard. So I was doing a lot of like formulation in here. I was just figuring out. So to type check a function, there's two different scenarios that you have when you're type checking a function. Either it's a normal function like this, or it's a closure. All right, and then so here are examples of two functions. So you have a normal function right here. Functions declared this way. These are the only functions that can be declared at top level, by the way. Functions declared that way, they have to have the arguments and return value. So you can't do any kind of like special inference of arguments and return values. But what you can do here with closures is the you can know the arguments, but you don't have to know the return value. So how I did before in the last I think this is when, yeah, this was a while ago when I just got closures working in one VOD or something last stream. See how I can call a closure with T here with 20, which means T is inferred to be I32. Yeah, so they've inferred the argument, which means you can go in and start inferring the return value. I32 plus 1 equals I32, which means that's how the type of T is inferred by this call here. Anyway, what I'm trying to say is these are two different kinds of functions that can be in the IR. And when this even gets attempted to get type checked, you know the types of the arguments. You just don't know the return value. So there's two different types. You can you type check a function with the return value, with the return type and arguments, or you can type check without the return type and only the arguments. So it's just two simple things. They're very similar. They're very similar. Okay, so root finding. This is something pretty important. So let's say you have, let's a equals u8 equals 10, right? If you parsed it, or if you did type checking, without this annotation, a would be inferred to be an I32. But if it's just like this, it'd just be a u8. What you need to do is you need to propagate this type information upwards so that 10 can be a u8 as well, and then that type of information goes down. I've talked about this in detail before in a couple VODs. It's pretty simple to understand. Just type information flows up, and then type information flows down, and that's very simple bidirectional type inference. Where it's something a little bit more complex, where it comes into consideration is, let's go in if cond 50 else 25, right? That u8 has to go up inside the if expression, and this u8 thing has to go inside the branches here, and then they come back down. Zaka says, could be inferred to be more than I32 if a constant is bigger. That's right, but it also adds in this like, oh, I don't know what my integer is going to be. How big is it? And things like that. What Rust does, and I use Rust as like a reference just because I don't know, right? Because they do a lot of things right. And I think Zig does it as well. I don't know of any language that takes a look at a integer literal and then makes it bigger or smaller. If it's too big to fit inside an I32, that's what Rust does. It raises an error, which means if you want to have a big enough integer literal, you have to specify its type, and I think I'm okay with that. Yeah, so the let a, you're giving it a type annotation of u8, which means u8 needs to flow up into the branches of these things and apply it here. Yeah, but if this wasn't here, no type information would flow up, and then a type of I32 gets assigned here, and then now type information flows down, and A gets assigned I32. Right, so this is bidirectional type inference. And this is what I mean by root finding. It's very easy to find the root of a tree, because you just have its root node. But if you take a look at this, it's easy to tell that A is the root. And when you find, if you have a root and you have the root's supposed type, you can bring the type upwards. So let me compile this and show you what I mean. This is proper root finding. Main does this, and here, this will be easier. Main nothing equals this. Okay. Let's just do cond. There we go. I did the right types. Okay. Alright, so let's put this side by side. So, function main. Entry is a bool, go to pattern. So this is all we really have to care about. %3 is the cond, so you're assigning cond here. If cond, go to if then, else, go to if else. So there's two things, if then and if else. And if then, 50, and you're returning it back here. If else, 25, and returning it back here. So where are the roots in this expression, right? If this was a node-based compiler, all you have to do, I mean, the root is essentially everything on this side. But like, where do you start with this tree AST? Where do you start? Because I have the return value. Let's say u8. This is u8 right here. I want to propagate u8 up here. But how do you do that? in a node tree, you'd have a reference to the root node, and then okay, let's just start recursing all the way up. That's what I did before in my last IO. But right now, where do you start, right? So I'll give you some pointers. So you know the type of this, and you know the type of this go-to pattern, because cond is known to be a ball. So here, cond is a ball. Okay, you know the type, you know cond's a ball. A ball has to go into the if, that's fine. But you know where another type could be. This U8, all the way back here. So where does that U8 end up being? Here, in the return. This is the return terminator, the last thing of a block. It has to either be like a go-to, a switch, if, but this is just a return. So you know the type that's supposed to be here. The type that's supposed to be here is a U8. So what you could do is, now you've just found your root, which means you can go here. Okay, I need to find the type of %6. So I need to go up here. All right, %5 is supposed to be a U8. Okay, go here. %5 is supposed to be a U8. Let's check type 25. Oh, not type 25. Let's check integer literal 25. Okay, that's supposed to be a U8. Yeah, it's supposed to be a U8. So it's just going here and this path, and then it also goes to this path as well. So it's just like before with nodes, where you have a root if expression, and then you have a branch for the then condition and a branch for the else condition. You travel to the then condition and the else condition, you get their types to come down, and then you unify them. Like you bring them together. And then you can check if their types equal, and then they go straight down to return. So the roots essentially, this is what I've come down to after a lot of thinking about how this thing works, right? So yeah, so this root finding algorithm assumes that the graph representation is the one generated by the parser, by the way, as well. Oh, there's specific things about it. Okay. Yeah, so type information with respect to the return and entry flows two ways: downwards from function arguments and upwards from the return value. Now, flowing downwards from function arguments, those aren't roots; they're just variables, but they flow upwards from the return values. So, what I'm trying to say is, in this program, every single return terminator that you see is a root. So you start from here and then you start recursing upwards. So we basically go bottom up. And that's exactly like the node representation. All this is, this control flow graph with instructions that depend on previous instructions, you can think of it like a graph, but a flattened down graph. So all we need to do is start at the return and go all the way up. Simple. That's simple. Yeah, so it doesn't matter what return you use. You just keep running passes on each one until you've exhausted them all. Yeah, okay, so all definitions dominate uses. If they don't, it's obviously an error. Like you're trying to use a variable before it's defined. So all definitions dominate uses. That's just obvious in an SSA thingy. But that's only obvious for SSA locals. But for normal locals, they can be assigned all over the place. But the first assignment always dominates all the uses. So all assignments dominate uses. You begin at all return terminators for all blocks. So all arguments to a terminator are roots. So you can assume, let's say I'm inside the if else 3. Let's say I'm inside this block and I'm type checking it. This is the terminator, the last instruction, or it's like a special kind of instruction at the end of a block. And here, any arguments here are roots. So %5 is a root, which means you can start type checking all the way up. Here, let me just do like +50, +25, do a bunch of pluses. Okay, so now you know for sure %9 is the root, because %9 goes to %7, 7%, %5, all the way up here, then %8, all the way up here. So you know %y dominates all of these things. Okay. Yeah, so when I say walk backwards, I mean essentially walk upwards, because we've been walking, we start at the bottom and we work our way up. Okay, so walk upwards. Walk upwards in a block, and for all instructions, follow the chain down and mark each instruction or assign a type. Okay, so yeah, so let's say %9 is the root. I check all of these things. Here, I check them all. But, yeah, so here, this would be a better explanation. Else do this. This is the last expression. All right, and let's just put this 40 here. Yeah, just 40, and it obviously is getting unused. No one's using it. Actually, just to clear. All right. So we're in the if-else block right now. We're working our way backwards. %10 is in the terminator position. It's one of the arguments, which means it is very obviously a root. So right now, we're going back here. We're checking this. All right. Checked all of this. %8, %9, %6, %7. All right, so we've basically done all of this, and we've marked them and given them a type. And then we go up one more. Okay, %5 has no... it has no... What is it? It's not being depended on. Since we marked this root here and we went all the way up, %5 is not being dependent on something, which means it's a root. And I can do something here, like 20 plus 40, and this thing applies. It goes all the way up to 8 here. And then, okay, we've exhausted everything pertaining to this return root right here. We go up one more to %7. Okay, since %7 is not being depended on, since %7 is not being depended on by anything further on here, and all definitions dominate their uses, so if we see its definition here, and it's not being used further on, that means we know that %7 is dead code. That's one thing. It's not going to be very important later on, but we know it's dead anyway. But we also know that it's a root, so we can start at this root and then type check recursively. So let's say like %7 has a type, let's say U8. We propagate U8 into here and U8 into here. And now we've essentially type checked the roots, so we can go all the way from the bottom up. And there's a way you can think of this, right? You can think of this as a flattened node tree, and I did explain that it's a flattened node tree. But let me put it in a way that probably make it easier. Yeah, so let's pretend I'm I'm unflattening the graph. So removing this, %10 can be inlined here. Okay, it can be inlined pretty easily. Okay. Zaka says, this looks like the same tree, but reversed due to SSA form. That's right. So when I go here, this %10 gets inlined in here. Okay. And then %9, all right, gets put in here. %8, put in here too. All right, and then we're done. Okay. It doesn't rely on any of these things. %7 has no uses further on. It's not used in here, which means we've just located a root, and then now we've located another root. So what we can do now is go here, %5. Okay, let's inline this. Okay, %6. Let's inline that. All right, take a look at this. We've located all the roots. So we have %7 is a root, and %12 is a root, and that's being used here. Now, we've essentially found all the roots, and we can start type checking. So %12, we can go all the way up. Let's say the resultant value of the if expression is supposed to be a U8. So that U8 is supposed to be here. This is supposed to be a U8 right here. Which means this type of information flows up. Which means, yep, so checking in here. 25 is supposed to be U8, not an I32. It's supposed to be U8 because type information is flowing up. 25 is supposed to be a U8, 50 is supposed to be a U8, 25 is supposed to be a U8. And then we've type checked this whole thing with type information flowing up exactly like it's a tree. And then here, %7. Okay, there's no type assigned to %7, so let's just give it the default type of i32. These flow up, i32 plus i32 equals an i32, and then we go all the way back down, %7 is an i32. It's simple. It's simple. This root finding algorithm of going from this tree-based data structure. So we have this tree-based data structure, which is our AST, or our high-level IR, which is before. We have this tree that we have, and then we can start at the root and go up, and then we propagate our type of information up. What we have here, though, is flattened AST, where all definitions dominate their uses. So, say you have a definition here, it's always going to be used. All the uses happen here. There is no uses before it's defined, which means all you have to do is walk backwards. All you have to do is walk backwards. Simple. It's the simplest thing in the world. And when I came to that conclusion, I was pretty happy. I was pretty happy. So, let's try it. I think that's it. I think you guys need a recap. I'll give a simple recap. Pretty simple. So, yeah, you're just going to unify if exit. These are the things here, and then here %12 is a root. So, %12. All of these are part of %12 all the way up to %8. So this whole thing is part of %12. And then %7 is now the new root. The new root. The next thing over is the root. Because if you haven't found %7 before, that means this is the last time it's not being used at all. So that means this is the new root. And then we found a whole new tree. Zaka says, no const folding or overflow checking yet on this type check pass. You mean like checking so I'm assuming you mean checking overflow at compile time. So that's one thing that you can do. I think we could. I'm not gonna do constant folding immediately. Because constant folding is gonna be in another thing. So I mean LIR type check. Or is it this one? Yeah, I mean, so this is so we're right here. We're at number 1. So we're possibly gonna do overflow checking in here because this is just like, no. I made up my mind. I'm not gonna do constant folding is not gonna be in here, and overflow checking is not gonna be in here, because in this you'll just check the literals for the range of the type. You're right. That I may do here, but I'm talking about something else that you didn't mention, but I'm going to mention it now. Let's say you have let a x is an i32 and it equals something, right? And then let k equals x plus let's say like a huge fucking value that just barely fits within the range. It'll be easier for me to explain with a u in. Yeah. 255. Okay. You don't know the value of x, so you can't assume that this overflows. But what about now? What about now? A simple, a very naive and tree-based optimizer will be able to see that, okay, there's no overflows that happen here. But if you have like an IO optimizer that puts things in this kind of normalized type, not normalized type, this like normalized IR. Let's for example, a normalized IR would have all the additions on one side and all the constant values on the other side. So that means it makes it easier for the constant folder to work. So let's say the optimizer puts it in normalized form, which means it replaces this with this. Okay. Now, it brings these together. Okay, now the constant folder checks here. Okay, this is very obviously a overflow. So these are some things that normal compilers won't catch, but they will catch if you have this complex optimization thing. That's what I want to do as well. That's something important, which I'll write here. But let me just put this right here. Conditional loop types. Conversion to 255 plus x plus 225. Okay, well, to answer your question, no constant folding in this pass, but the overflow checking, we will check that that the string literal, well, not the string literal, we'll check that the string representation of the integer fits in the type. We can just check that, but anything more complex, we're not going to do. What would happen to later passes in case of let x u8 equals 500? No. So we aren't gonna constant fold this. We're just gonna raise an immediate we're gonna raise a compile error. We're gonna raise a compile error for this. There won't be a let x equals 500. There will only be this can't happen. It'll raise a compile error because we're not gonna let that code being generated. That's a very obvious undefined behavior. It's trivial undefined behavior. Okay, so I think I explained enough. We can get into it. So all we're doing is root finding. Not the root finding like Newton's method, but finding the roots of a graph, but a flattened graph. Like if you have a graph, you already know where all the roots are. We're gonna find them ourselves. So we can start at the very top here. All right. Yeah, proper root identification. Yeah, I was just writing a whole bunch of shit. Okay. So begin at all ret terminators for all blocks. Okay, so what we need to do is, so this is the last type checker. This is the last type checker. Yep. Yeah, I removed the .c because I didn't want it to be used by my build script here, which is my very obvious build script, which is a one-liner. Do you store the ID of an instruction when you reference values? If you're referencing like, here, I'll show you. So let's say you're referencing %12. Since it's an SSA value, it always has one definition. So you don't need to store it. You can just linearly search. And that's what I do for call merging. That's what I do for call merging. I go all the way at the bottom. And I perform call merging. So since I have a expr.value.local, so I found a local, right here is a local. I can find it. I need to search linearly. And if I find it, I remove the instruction at this. So this is the result of the finding. So you find an instruction with this local here, it returns this result, and it returns the block that it's in and the instruction index, and returns a found. Yeah, so that's what I use. An SSA local always has one definition, so you know exactly where it's being defined at all places. Okay. So, oh man, this is a big hunk of shit. This type checker. Good thing. I had more time to think, so I know how I want to structure this. All right, HIR check modules. See top level expressions. Okay, and then runs through every single expression in the top level of a module. So first, this is something I want to type check. This is the one thing I want to get done this stream. This is something I really want to type check by the end of this. This one. All right, this factorial. Okay, simple. All this is n equals if n equals 0. And then if it equals 0, it's 1. Else n multiplied by recursive call to fact n minus 1. And you can remove these parentheses. Actually, no, you can't. Yeah, this is a function, right? And when you run it, generates an entry block, pattern 1. N is something. Yeah, so it compares n to 0 if n equals 0. And then go to if then and if else, %6 equals 1, if exit, it jumps down here. So if n equals 0, jumps here, goes to if exit with 1, returns 1. If it goes in here, %7, you're calling %7, that's main.fact, because you're calling, and it's an external symbol. That's why it's got this weird syntax. Yeah, and then it just does computes the next value by multiplying, and then just returns. Pretty simple, very straight line. There's only one return, which is right here. Okay, well, let's start. So, what I should explain first. I'm going to explain this first before I get in. There's something that I did, and I talked about it inside announcements. I said basic topological sort on symbols plus red expression. So, what this does, let's say you have these three functions here. And then we'll just, here, so inc double takes in a tuple, returns a tuple, runs a function on the internals of those tuples. Ident, so it's an identity function, takes in an i32, returns an i32. Inc takes in an i32, equals calling the identity function on x and then adding that to 1. So that's equivalent to just this, but I'm going to make it a nice example. So which way does it type check? Does it go top to bottom? It obviously can't, right? Because when I hit something, I want to know the type of it before. So what I do is, here, this is the type checker. So when I call LIR check, it calls this thing called C reorder. It's here. So there's a list of symbols. LIR sim. This is a reference to a symbol. LIR sim t. This is the LIR sim t. This is the symbol. So key into hash map is the fully qualified name. The fully qualified name is what you see here, main.fact. What was I looking at? Fuck, I'm blind. Okay. This is a reference to the module. This is the reference to its short name. Its short name would be just fact here. Is placeholder, is visited. This is instead of storing a set of all visited nodes when I do my topological sort, I just put it here. Yeah, and that's just type, and then a kind, globals, procedures, and types. If it's a procedure, you got your proc here, or a function. Same thing. And all it is just a list of symbols. Global variable. I don't care. I'm not ashamed. I don't feel ashamed for using global variables. This is my global symbol table. So you can go here. Calling table resolve. And it's pretty simple. So the symbol table works with a sort of eventual consistency, where references to a symbol inserts a placeholder, and then later on we fill in the details. After the parsing stage, we go one by one on each symbol and check if it isn't a placeholder. And if it is, we raise an error. Zaka says, is this done to reduce the amount of recursion? You mean the topological sort? So there's a reason why I'm sorting declarations. I'll get into it. So before I type check, I need to know the type of it before, right? I could recurse, right? But I mean, what's the point of that, right? I'd rather have everything sorted perfectly. It's not to reduce recursion, because a topological sort actually does another thing as well. It checks for cyclic dependencies. So let's say you have y equals x, then x equals y, right? Which order are they supposed to be in? You don't know. There's no way to know because it's a cyclic dependency. The topological sort also checks that. So it does two things. Yeah, so these are the symbols. So this is the symbol from top to bottom. Symbol one is inc double. Symbol 2 is ident. Symbol 3 is inc. Okay, and what the topological sort does, so it goes here, inc double. Inc double depends on inc. Okay, so this can't go first. Okay, inc depends on ident. Okay, so inc can't go first. Then ident. Okay, ident doesn't depend on anything. So this original ordering of inc double, ident, and inc, the sorter goes, okay, let's put them in a way that they're not depending on each other. So ident, and then inc depends on ident, and then inc double. So it type checks ident, it type checks inc, and it type checks inc double. In my compiler with modules, this sort won't work probably. It'll work. I have modules in my compiler. And these global symbols, they are unique per each symbol. You could do some like file system trickery to like, because modules work by file system, so you could do some like file system trickery to like make symbols conflict, but then you get a compiler error. In short, a symbol, the global symbol, the fully qualified name, the main.fact, is unique. So I don't have to care about modules because the module stuff is already encoded inside the fully qualified name. So when I get to here, all I do is I just call it on the table of symbols. I go one by one through each symbol. I don't care what module it's in. I only care about the fully qualified name and what symbol they're actually referencing. This works without modules at all. I have full-on modules in my language. I've copied Go's or V's module system because I really like it. I really admire it. But it'll work. Trust me, it'll work. But the only reason why I need this topological sort, you see how all of these are functions, right? And their types are known. I technically don't need to do a topological sort. I don't need to do any topological sorts at all. Because inc, there's no inferring inc, right? You know, I wish I could change the syntax, do some inference, right? I wish I could do that. But anyway, right now, you don't need to sort them. I literally do not need to sort them. But what if I have globals, right? X equals 20. You don't know the type of these globals, by the way. I don't know the type. I don't know the type of these globals. Yeah, so you say, well, no. Sorting of functions, I still need to go through them linearly. I'm still going to go through them linearly. It's just the order you do them in. So I'm still going to go through these linearly. The only reason why I'll have to do them out of order is when you don't know the type. So for globals, I don't know the type of these things. So that means I'd have to move this to the top, right? But for functions, what I'm gonna do anyway is go linear. Right now, I'm just doing it sorted. That's just what I'm gonna do anyway. So it's fine. Okay, so that's what the topological sort does. It's pretty simple algorithm. Oh, that's so funny. So sorry. I did some I don't know what it's open chat GPT replacement thingy. I just looked it up. And I also looked at these things like finding the roots in the directed graph, algorithm for topological sorting. To perform a topological sort, there have to be no cyclic dependencies. So you have to like modify the algorithm a little bit so that you can detect cyclic dependencies, and that's what I've done here in the check reorder. All the way up to the top, and here's like type function global. Types are dependent on other types. Functions are dependent on types in the function signature and dependent on globals. Globals are dependent on their annotated type, and globals are dependent on other globals. Okay, so, and this is here function dependencies. In short, functions can't depend on other functions under any circumstance. It just can't happen. And I just talk about cyclic dependencies and specifically how top level, these already have applied types. Yeah, and what I was going to say is here, so visit dependent, if it's a placeholder error, but here, yeah, so say it's impossible to self-recurse into incomplete functions, here, and then here. If symbol is visited, cycle error, and I haven't given it a nice error message, I should, but later on, because I'm a little lazy right now. Be here, cycle error. Simple as that. Alright, so, let's get this function checking. Right now, let's get it checking. Okay. So, what we need to do is we need to find roots, right? And there's all the roots are going to be the return values. The return The return terminators. Okay. Check. Case symbol proc. So what we could do is, yeah, just name it here. LIR, just C proc. Okay, and yeah. Wow. Okay, thanks for the boilerplate. All right, C proc, and then just C proc I. LIR. All right, LIR SIMT, and then you are just type checking. You just print off here. Let's bring up main as well. Cool, LIR check. All right, run. All right, and then we get here. So we need to locate all the returns. So let's go. LIR block TI 0 C. You know what I should do? Zaka says, I decided to submit to OOP style and add methods similar to Zig methods. Well, methods on a struct, like having functions attached to structs, that's not OOP. So there's a distinction there, but so that's technically not OOP style if you just have methods, but if you're doing the rest of OOP, that's obviously OOP. Okay, well, you know what I should do? They can force OOP thinking. I don't know. Any kind of I don't think methods are OOP at all. They're not. OOP has a bunch of things in it, like encapsulation. No, well, encapsulation is good, but there's like inheritance. There's no like inheritance with methods. So this technically not. Well, it's not. It's not OOP. Yeah, I don't consider them OOP. You could create a crappy object hierarchy when you have methods. Well, it's basically the same as normal C. It's basically it's like a syntax trigger for normal C functions, right? I could define cproc on an rsim and then call cproc like that, right? But it's essentially equivalent to that anyway. I mean, you can make the argument that why even have functions at all, right? They're just a syntax trigger. Okay, well, what would be good is if I had a macro that did this for me, and then I'll go replacing it throughout the rest of the functions. All right, define, not ds, but LIR for LIR blocks, right? How does quick do it? Get quick. Okay, let me just steal that. Just steal that. Steal this. Steal it all. Same at 4 blocks. Proc block. Yeah, I'm gonna quote that. Block, proc, and then block plus plus. All right. Okay, 4 blocks. 4 blocks. I need a proc as well. So let's extract the proc. LIR proc t equals is that address? Yeah, it's address of. Adding symbols as well. To so these pointers are unstable at all, but good thing we've already finished adding to the symbol table, so we don't need to create more symbols. Let me just write a note here. Note. We won't really need to anyway. All right, 4 blocks. Proc I. Isn't that nice? I love macros. So if I need to do PTR as well. For blocks PTR. Can you touch on how you represent globals in IR? Is there a block for the expression of the global? So, I think you mean how globals can have this complex representation. Let's say you have global equals fact, right? It's just calling a function. So, in the IR, nope, clear. So this is an example of some IR, right? It's an example. Create a new thingy. Okay. What the hell is this batch? It's technically this batch. Okay, so I was gonna have something like this, like function, and then like global main dot global, and then it is literally the body of a function. So it's still gonna do. Oh wow, it fitted in for me. It's gonna be a body of a function, and it will be computed at compile time. Or I want certain things in my language to be computed at program start. I want to make a distinction there as well. But the compiler will treat these are symbols. These both are symbols. So it will topologically sort this global all the way up to the top. Oh wait, no. If this global was at the top, if let's assume the global was at the top, it'll topologically sort it all the way down to the bottom, and then type check main.fact, and they go all the way down here, and then type check, and then also after type checking, check if it's a constant expression. So it knows to have a main.fact because it type checked it. It'll go here, do constant evaluation, and then return. Simple. So I represent globals like functions basically, but there's only one. It's like a function but with one basic. Well, it's like a function but with one return. A function but with one single return. That's what it's like. That's what I'm doing. So I represent them just like functions, but they're computed at compile time. So they're still in this because a global can have control flow as well. Like if c equals 20, if c, and then so you'd need to first reorder, and then you'd have to there's control flow. So this is what Rust does. So anyway, for its mir mir. And you know what? I could do some kind of like Zig comp time system, right? That would be really cool. To have like global is a type of I32, which is let's make this 2 and then 1 2. Right? I could do that because I could do that. I could definitely do that because the order after the topological sort, it'd move this C to the top, and then when it gets to here, it references C, a global symbol. Ah, fuck. That's cool. Okay. I can add like in my types TI kind, type kinds. Or is that types? Length, I can make it like bool is symbol. And then symbol. Food for thought. I'm definitely doing that. Because I have the functionality to do that. Okay. Let's I think that's enough information for you. If you have any more questions, you can ask me. I'd be happy to help. But time to implement. So let's just find all the roots. So I'm gonna do four blocks PTR as well. 4 blocks PTR. If you have arrays of constant size, those constant expressions also become same IR with the requirement of a constant evaluation. Yeah, because you have to check that the value on the right hand side conforms to the type on this side. So so constant expressions are IR. There is no other representation of a constant expression other than IR, right? So it'll reorder them, C's at the top, and then it'll go down here. it'll type check here and then like type check, try to unify with the equals, and then it'll check if they're the same, so that they all require a constant valuation. Yeah, the constant array expression is just IR. Okay, 4 blocks PTR because we want the PTR. Block PTR. To type check arrays, you'd have to constant fold. No. I'll show you how an array is represented. Main do nothing. Just keep doing nothing. And let v equals 1, 2, 3, 4. And then let's just make this k. Just 49. Okay. And let's see. This is an array representation in the IR. So let next. This is basically here. You're at v. And here, percent 6, percent 7, percent 8, percent 9. This is 1, 2, 3, 4. The k is being assigned here. Okay. Percent 10. You're constructing a array literal with percent 6, percent 7, percent 8, percent 9, and k. And then you're assigning it to v with this go to pattern construct. There is no constant folding. All you have to do is, when you get to here, so going back to what we were talking about at the start, 10 is the root, go to 10. Okay, we're going to type check this, and give me all the types. Okay, we're going to make sure that this type equals this type, equals this type, equals this type, equals this type. And then, if all the types are unified together, that's the type of the array, right? Right, so given roots, we can go all the way like that. So no constant folding needed, you just type check. Just type check the elements and then you perform a unification. Yeah. My arrays have different syntax. Array literals look like this. Constant expression, I32. I need to check of the size matches the constant expr. Well, you'd need to check that the inside of the array equals an I32 as well. But yeah, you didn't mention that. But also, yeah, so you need to check that the size matches. Well, yeah, that's also right. That's also right. Are you trying to decouple? Are you trying to decouple a type that depends on a constant expression away from like their actual types in the type system? Oh, I don't know. That probably doesn't make any sense. But you don't treat const expr array I32 as a type on its own. Oh, I don't know. Sorry, I'm just yeah, you'd have to do that. You'd have to do that. All right, fact I32. Okay, 4 blocks. Okay, 4 blocks PTR. Just fill it in for me because I'm not bothered. Okay, proc blocks. Oh yeah, array literals cannot specify any types and be inferred. Okay. That creates some const dependencies on those expressions of sizes. Cluster language. Okay. Yep. For syntax, for my language, what I want to do for specifying a type of an array is I want to have, let's say this is an array type 5. I want to perform casting here to do that, right? I want to like, because this is the cast operator. And since type information flows up, I use bidirectional type inference, this cast will be evaluated. Okay, this is 932. Let's push this up into here. And then like you can do like this array view weight. This was possible a couple streams ago when I had the HIR. But that's how I want to assign types to those. Okay, 4 blocks PTR. And we'll go like __ end PTR. Ends PTR. Okay, 4 blocks. Okay. Under any don't realloc. Actually, we will be reallocating. Okay, so we just forget it. All right, 4 blocks. Proc LIR block. Okay. If b dot terminator dot kind equals term ret root. We found our root. Okay. Now we need to. How it works is begin at ret terminators for all blocks. Okay. And now we need to create a function for type checking a block. We can do that pretty simply. Void LIR proc t pointer proc and so LIR r block t block. Yep, and then check block. Else continue. Is that right? Well, okay, we're continuing anyway. There's no need for that. Alright, root block. Okay. Proc and block I. Okay, and C block. First, I just want to print the name of the block. What information do I have about it? Do I have like a debug name? Okay. Alright, and then %s will just return, we'll just print nil. If it's null. Okay. Now, what I don't want is, okay, we'll go to main. We'll reorder this. Put check first. Okay, block 4, if exit, that's it. That's all the way at the bottom. So, let's bring in our rules. Okay, that's a lot of rules. We'll make it simple. All arguments of the terminator are root. I walk upwards of the block. Okay, well. SSA are roots. Yep. When reaching a parameter to a block, recurs to without values blocks edges to share the current one. Okay, we'll just cut on some line length. Okay. Well, I think I gave one of the best explanations I could at the start of how this thing works. But we can start by saying all arguments of terminator are roots. So let's just find all the arguments. We know those are roots for sure. So we can go C inst check instruction. Yeah, check instruction. C inst R block T block. Okay, so we need to switch on the terminator because there's multiple different terminators and those all can have returns. So let's find all the terminators. So we have term uninit. It shouldn't be that. Term goto, term if, term switch, term ret, term goto pattern. So switch b dot term dot kind. And have all of these things. And then default. Okay, what are we actually using? We're not using switch. We're only using these. And then what I want to do is I want to extract this out into a function as well. So cblock, cblock terminators with the value LIR local t. So it's value, values, values, and then LIR term block t. So this is a terminator, which can have a block and multiple arguments. So that's how goto works. Okay. Term, and then we're just calling it with a LIR local t value. So it's a goto pattern. Let's just do it as a term ret. That's the easiest. Term ret b dot term dot dret dot value, and then we're calling it on C block term with proc block and break. All right, goto pattern, same thing. There's only one value here. D goto pattern dot value, and then if. So now there's two cases. Now we have where we assign the basic block parameters. So we need to go C block term inst, and then a C block term for a block terminator. So we have LIR term block t, because the terminator can have arguments. And then for term dot args I is less than c, I plus plus. This is really a pain to write. Okay, let me move this all the way up. Simple. Then I call C block term inst. So no, because that goes up here. Right, b term the if cond else and then what's an if statement look like? I forgot. I can't believe I forgot. Okay, so let me go through it now the way the compiler would probably do it. So starts an if exit for 12 is obviously the ret. Here, let's go to here. If then, and we'll go here. Oh yeah, that's right. Okay, well, see how it says there's no arguments here? Code generated by the parser for if branches, exclusively with ifs, there is usually no values flowing into them. If 0 arguments. If usually has 0 arguments flowing in. So we have else, then, and else, and then we need to check C block term. No, C block term inst. Yeah, the cond. Right, if usually has 0 arguments flowing in. Okay. So now we have all the terminators. Now we need to find out where this is from. We'll create a function for finding. Oh, that's just for terminators. Okay, yeah, so let's say the terminator here is %11. We gotta find, okay, is it an argument or is it a local, like defined? So we can start like this. Ensure value is is defined here. Okay, so what's important is this is okay. What can happen is what I'm worried about. What can happen is, let's say if exit and then 12 doesn't get from here, and it's just like a immutable, like f, right? It's an immutable. That means this value would not reside in here. Okay, so uses of f or uses of a value can never be roots. Okay, so proc locals. I'll name this value. Also, I have a. Oh no, okay, I don't. Okay, local. What was I gonna write? Kinds equals okay. LIR local SSA or im. No type can be ascertained for locals. They for yeah, and what I mean is what I basically mean is, let's say we have ret12, and then let's just say like f equals something, right? And then we're using it here. Without even seeing the top, and let's say ret is supposed to be a u8. We can't really propagate this value up because we're just using it, right? Variables always have a definition. You can't like propagate it up. Like you can't infer a variable's type from its use. You can only infer a variable's type from its initialization or assignment. So that's what I need instead. I only care about SSA locals because they only have one def, which means you can propagate the value up. Yeah, that's basically it. Yeah, just to avoid code like this. Let's say like someone goes let a, and then if a, and then a like, okay, you're supposed to have a bool here, but you're using a before it's assigned. You know. So it is nonsensical to even attempt that. So not equal local SSA return. They have their own defs. Hold on. All right, let's get back to it. Now I need to think, because now we found an instruction which is the root. We need to recurse upwards. So let's just create a little example here. All right. Ret 12. You would need to, and let's say this is like a tuple. This is malformed code, but just assume it works. Let's assume these are, this equals f, right? And f is defined all the way up here. Okay, so what we would need to do, if you're doing this naively, you'd get to the ret, and okay, this would be called with %12. Alright, so now we need to start recursing all the way up. But, in the definition of %0, f is being used. And f is being going all the way up here, and that, like, when it reaches 12, it'll work, right? But if it's reversed the other way around, no. So f gets defined if we're using the variable f here in the definition of %0, but %12, if you were checking %12, you'd have to go all the way back up. So if you go naively from left to right and check %0, and you're using it here, you won't know the value of f until you check here, because only when you check here it goes up. So you need to sort these things. You'd need to sort them. Yeah, you'd need to well, actually no, I'm wrong. I'm kind of wrong. Kind of wrong, because that assumes that this syntax is right. Okay, %1. But then, okay, well, so that still causes the same issue, but... I could do this in a two-phase. I could do this in two phases. Let's assume that %1 has to have a type of I32U8. Okay, so in the first phase, it'll check %1. It'll go in here. Okay, it's supposed to be a tuple. It propagates the type I32 up to here and propagates the type U8 up to here. Okay, it'll type check this and then this. Um, hmm. This propagation stuff is hard. Okay, I have an idea. We do this, we recurse up, then we reach all the way bottom, and then we start type checking. Okay, so I'll explain. So, we have a whole basic block here. It has a return terminator, this is a root. %1 is a root, so we're going to start recursing all the way up. What we do from here is, we try and find... We essentially go through the program. We don't type check these %0 and %1. We go here to %1, and then we like kind of half check it, but we don't assign a type. We only assign an up value, and let's say the up value is a tuple of I32 and U8. So I32 goes here, and U8 goes here, and then we assign U8 here, and then we so this is two phases. Assign up values to prop upwards. 2. Propagate upwards. 2. Recurse upwards. So I'm recursing upwards, and then I calculate the current block. Okay, so this is where it happens at the start, and we know this up value is here. So this is step one. Well, this is step one. So now we know that this is supposed to be this, and then we assign this to a U8. So we know that's true. And then now we recurse upwards with this value. Let's say f equals percent 12. This is completely nonsensical as well. But let's just say x equals, oh, like you just do like a, let's be a terminator. Go to if exit with percent 2 equals 0. Okay, so the first thing here, and let's just assume that percent 1 has an up value of I32 and UA. Percent 1, so you unpack them. I32 goes here, okay, that's fine. And then U8 goes here. This is a parameter, and that means you can recurse upwards. Yeah, so the recursing upwards, that means percent 2 is supposed to have U8 here, and then we get to here. So what we're essentially doing, in like the simplest of terms, is we're flood filling the program. So we're going to flood fill from the bottom, and then flood fill down. It's kind of this how do I explain it? We're essentially flood filling. Yeah, okay, this will probably help. This will help. Okay, so let's just assume that main fact has the signature of U64 to a U64. So ret has to be a U64. So we know this. Percent 12 has to be a U64. And we propagate this upward into a U64. Okay. The two places that go to if exit, there's an if exit 4 and an if exit 4. So we know that percent 11 is supposed to be U64. And we know that percent 6 is supposed to be U64. Okay. We propagate this up here. We get to here. Okay. Percent 5 is in the bool position. It's supposed to be a bool. And then we are basically done. This is pass 1. We propagate upwards. And then what I think we do, let me go back down. Veek7 says, what do you recommend for learning compiler after the crafting interpreters book? Working on a programming language for the game AI scripting. For game AI scripting. And I'm wondering about the IR thing and whatnot. Would love to jit it someday. Okay. So, after the crafting interpreters book. So I haven't read the crafting interpreters book. I've read a couple pages of it. It's a pretty nice book. Now, how I learnt compilers is essentially not much of reading code, but Wikipedia articles. That's like one component, but it's essentially like it's like I'm standing on the shoulders of giants basically. So there's a ton of compilers out there, and they follow a certain compiler model, right? Look at Clang. Clang compiles to it. Clang turns its syntax into an AST, and then into a LLVM, and then out. GCC, there's like a couple stages. GCC to like Gimple, there's like tree Gimple, and then goes down to SSA Gimple, and then RTL, and then out. You just need to, you say, I also type check my language, the book didn't cover that. No, that's right. So I assume you're type checking based on an AST going tree all the way up. Where could you go from there? You're wondering about the IR thing. So you're wondering about the IR thing. So there's a very simple thing you can do. You could convert, so let's say you have an AST. There's a couple ways you can go. You could convert your AST into a flattened representation. Let's say you have A equals, and not in Microsoft Bash. Simple language AST type checking is fine. Yeah, that's right. So let's say, this is for an IR. Let's say A equals 20 plus 50. B equals A plus, like, 23. And then what you could do, like, generating IR for an AST is pretty simple. Python does it very well. there's two ways you could go. You could go for a stack-based model. So you could go like, so let's say from the eye of the compiler, it sees this expression right here. A equals 20 plus 50. Okay, so it recurses upwards. It reaches 20. So push 20. Okay, it reaches 50. Push 50. Okay, so it now has to put them together and then just add, and then pop A. This is the simplest intermediate representation you can do. This is a stack-based implementation. Python does it. All it does is, let's say you have a binary operator. It has two expressions, right? You recurse upwards and generate them, and then you recurse upwards and generate them, and then you generate the op here. So it'll go here, recurse this way, generate 20, recurse this way, generate 50, and perform the op for add, and then pop A because you're assigning. This is a very simple stack-based IR that you could do. It's very simple. Python does it. You could go. It's not a very fast IR. Yeah. Veek says, yeah, that's how stack-based bytecode is implemented. The book covered that, but what's next? I wonder. Yeah, sorry, I haven't read the book. Yeah, I'm sure the book covered that. Okay, so what's next is a register machine. You could do a register machine. Let's assign so you're gonna go up. Let's say you have a expr function that takes in a IR node and returns a IR value. Let's say this IR value is a register. So let's take a look at this code and let's generate it. So R0 equals 20, R1 equals 50, R2 equals R0 plus R1, and let's say A equals R2. So what you've done now is you've flattened the stack-based representation. This is a register machine. Lua uses this. Lua uses it. But what you could do is then perform optimizations. You don't need this R0 temporary. You can put that here. Well, you've essentially you've essentially optimized it enough. But what you could do now was constant folding. So let's check the value of R2, and then R0 to here, and R1 to here, and then add them together to R2, and then A. Oh, hey chat. So Lua or LuaJIT? So only Lua. Lua uses this register-based representation. What it would work like, assigning to a value would probably be like locals A. It'd use some kind of like tree operation on the left-hand side, some table operation on the left-hand side. But so what LuaJIT uses is what is it? I'm trying to remember. It's two representations. It uses the register representation. It's way more sophisticated than normal Lua. But what LuaJIT does is have two representations. A register-based representation, which is fast to interpret on, and a SSA-based representation. So it would just convert these into SSA. Did I say something else? I mean SSA representation. There's two different representations, but Lua only has the one. Veek says, I did some const folding on the AS tree, but I don't figure it's very optimal. Yeah, so I was talking about this before a little bit on stream. So let's say you have this 20 plus B plus 30. Okay, you cannot const fold this because you'd only be looking at these right here. But when you generate register code, equals 20, R1 equals, R1 equals B, R2 equals 30, and then R3 equals, was it R0 plus R1? And then R4 equals R3 plus R2. Locals A equals R4. Okay, so let's just say that's the output of that code generation. But what you could do, what optimization you could do, see, you cannot const fold this. But there's an optimization that some compilers do, all compilers do. This is called reordering. I think it's called like putting something into a normalized form. What you would do is you would do that because addition is communicative, commutative. I think. But if you have an SSA representation here, so this is a register machine. If you had an SSA representation, you could just reorder them. There's a specific, I don't know the in detail about the optimizations. It's one I'm going to implement in this language, but I don't know the specifics. Uh, what you should do though is if you want to go further, sorry, I'm dragging this question out a long time. If you want to go further, you should look into SSA. A simple place to start is this register machine right here. There's specific optimizations you can do. You can easily find dead code. Let's say you have 50 here, 50, 24, and then just like R5 equals 50, R6 equals 24, and then you'd go all the way down here and be like, okay, what references R5? And by the way, this is technically static single assignment form. When I say static single assignment form, I mean every single register, think of them as registers, has a single assignment. And I can extend that definition by saying all definitions dominate uses. So the definition of R0, this goes first. It dominates uses. Okay? The definition of R2, this goes first. It dominates all uses. What you can't do is do this, because that's not static single assignment form. That's not the way that you generate it. So I can extend that definition to all. So SSA is a form where all definitions dominate uses, and all definitions are only defined once. So you can easily check here. You see R5? Does R5 appear anywhere down here? No. Delete it. See R6. Does R6 appear anywhere down here? Delete it. It's as simple as that. And there's lots of optimizations you can make on SSA, specifically to do with like dead code elimination you get for free, constant propagation. You can do conditional constant propagation with phi's. You can do really easy register allocation for the JIT as well. If you generate a SSA tree, an SSA, you can easily JIT it on that, because we can merge and control flow. You can do a simple linear allocator, simple linear register allocator, and just JIT it. There's another way if you want to do JITting really fast. Now we can go back to this stack-based representation. What you could do, and this is what I did for one of my programming languages. I made a programming language called Staz. It was a stack machine. What you could do here is you could have a register allocator, and let's say, I'll translate this code to x86 assembly. Mov rax20, mov rcx 50, mov rdx, oh wait, no, you're gonna add rax rcx, and then mov a rax. Okay, you could do that. And how you come to that conclusion is, I'm oversimplifying. Converting this to x86 should be done something like this. Push 50, push 20, push 50, pop rax, pop rcx, fill that in for me, push rax, pop rax, mov a rax. So you can easily generate these things. Yeah, this example is a pretty good example. But yeah, so push 20, push 50, add pop a, and this generates to push 20, push 50, pop rax, rcx, and then you add. So this whole thing is the add operation, and then this whole thing is the add operation, and then you're popping it for storing. It's very fast to JIT. It's the fastest thing in the world. You don't even need to build up a separate push and pop representation. You can just recurse the tree and just build in build operations. Now there's a project that I did a while ago. It's called what's it called? JIT calc. L1 MEY112 JIT calc does the exact same thing. You could use it as a good example. It builds up in wait. It's 112. You use this as an example. It builds up a tree. It builds up an AST tree, and then all it does is just generate code right here. Who needs an assembler when you are the assembler? Yeah, so look at JITcalc. 10 minus 5. And then it builds up an AST tree. So it moves rax 5, neg rax, move RCX rax, move rax 10, add rax, RCX ret. Super simple. So how do you convert? Vic says, how do you convert logical registers to actual ones? You can't. You can have infinite logical ones, not physical ones. Now this comes to So let's say we have some SSA. R0 R3 equals. Fill it in. I'm lazy. A equals R2. Yeah. So how do you convert logical registers to actual ones? So you can have an infinite. You can have an infinite amount of these R0, R1, R2s. Infinite amount of them. Now what happens is there's a thing called a register allocator. It goes through one by one and checks. Okay, what variables go in what registers. And if so, obviously the register allocator keeps these registers, like, let's say, okay, these registers are currently live. There is no more registers. All right, just assume this architecture has only 2 registers, and we've exhausted them. So when it gets to here, okay, we have to spill this to stack. So let's say this only has 1 register. Okay, so we could translate to this: rax equals 20, mem RBP minus 8 equals rax, and then rax equals 50, and we need to use it again, so we can't use it. We need to use rax again, so we need to store it. We need to store this to memory, and then and okay, we'd need 2 registers if we'd ever want to do addition. So let me just add something here. R3. R3 equals 75. R2 plus R3 equals R4. Alright, so let's just start translating this one by one. Rax mov rax 20. Mov RCX 50. Actually, this is also trivial as well. Let me move this upwards. This is also trivial. Okay, now when we get to here, okay, obviously, a compiler would do this reordering, but for all purposes, I'm gonna demonstrate the thingy. Okay, rax. Okay, now we're dumping the value of 20. Now the registers that are live right now are rax and RCX. Rax stores the value of R2. RCX stores the value of R1, and then you'd go all the way down. So okay, this gets dumped to stack. Also, yeah, you'd keep like you'd keep a representation. So let's say we have values. So R0 is in RBP minus 8. Okay, and then R1 is in, where's R1 in? R1's in RCX. And then R2 is in rax. So when we get to here, we have this sort of like table. This is a very naive example. A linear register allocator will go top to bottom and assign things directly into the instructions. But I'm just making a simple top to bottom linear register allocator for a super quick JIT. So yeah, so let's say we're at here right now. Okay, this is our current table, and then okay, let's execute R0 plus R1. Okay, so now we need to get the registers R0 and R1. R0 plus R1. So where is R0? R0 is in here. R1. Okay, we need to get R1. So we already have R1 in RCX. So we need to use rax to access this. So let's move this to memory. Let's move move RBP minus 8. Move rax into RBP minus 8, and then we can move RCX. No, we need to like. We need to clobber it. No, we need to clobber. Okay, so let's create a new stack. Hold on. This is getting complicated. Move RBP minus 16 to rax. Okay, and then move RBP minus 8 rax into there. And then perform the add rax RCX. And then when we finish this operation, the adding operation, what will be here is R0 is in RCX. And rax no, Rax is RBP minus 16. And then we'd have a free stack slot. So would be like free, we have RBP minus 8. This is a very simple register allocator. You have two different things. You have your list of registers in use, live registers, and then you have like your free stack slots. You can use them there for free. It's just things like that. Veek says, and when you need it back, you take from stack, I guess. And I guess you need to keep track of what will still be used and what will not. Yes, that's right. So you have this sort of like table. You have this sort of table, and you go down what values and what register and sort of things like that. It's a very simple explanation, but this sort of table with what virtual registers are in what registers. I mean, these are used in JITs all everywhere. JITs everywhere. A good example. I mean, you could use this code. I doubt it still works today because V's changed quite a lot, specifically with its C interrupt. But all it is, it's pretty simple. Gen. Here it is. Node expr. So this is a tree in the expression. So it goes to num program move 64 racks, and then here, let's say we're generating an add. We're adding racks to RCX and just all these things. Super simple. I can even put this down here. Yeah. Git calc and status. Yeah. Sorry, this is super long explanation. Super long explanation. But I think that was good enough. You know, there's multiple different paradigms or multiple different IRs that you could use, right? You could choose register, stack, and then you could also go to SSA. But there's also a trade-off. Building up SSA requires some computational effort, but if you just want to generate JIT, like you have to take into account the time it takes to generate the code and the time it takes to run. So let's say generating SSA takes a long time, but runs really fast. Generating stack-based code takes barely any time, but runs really slow. So there's always these trade-offs you have to do, and the reason who decides to make those trade-offs is a what's it called? A profiling JIT compiler. It's like some called like a tracing Git compiler. A tracing JIT compiler makes these decisions. It makes these decisions. Yeah, it makes these decisions. So for you to go, I just read a whole lot of Wikipedia. Really, everything I know about compilers is Wikipedia. I know it sounds stupid, but it literally it is. There's not many things on YouTube about compilers and everything. You know, you should like imagine like if I wanted to know like how Lua works. So look up, okay, the internals of Lua. How does Lua work? How does LuaJIT work? How does V8 work? Yeah, and you talk about V8. Chat says V8 is a tracing JIT compiler. Yes, it is. V8 is a tracing JIT compiler. SpiderMonkey, that's what Firefox uses. JSC, JavaScript Core, that's what they use as well. Yeah, so what a tracing JIT compiler would do is, he said, does V8 use multiple approaches? It does. I read the V8 code. I think it uses something called like turbofan or something. In short, it has two different modes of compilation. So when you're first running, actually, I think it only does this for WebAssembly. Okay, it only does this for WebAssembly. But for JavaScript, it has three different approaches. I think I'll explain the WebAssembly one because that's the one I'm most familiar with. When it gets a WebAssembly binary, WebAssembly is in simple stack operations. So all it has to do is run really, really fast over the code and generate dumb code. But at least you have generated code already. So it has two paradigms. One is compile fast, run slow. Two is compile slow and run fast. So it starts with the first thing. It compiles fast and runs slow, and then the tracing JIT compiler will say, okay, where's all the hot parts in the code? And then now we have to promote the slow allocation to a fast one. Slow so the slow the slow code to a fast code. So it would run the slow compiler on it. It would. All the tracing JIT compiler does is find hot paths and upgrade them. It maximizes both time it takes to prepare the program and time it takes to run the program. That's what it maximize. There's always trade-offs, these things in JIT. You know. Alright. The example took too long. Sorry. I really enjoyed answering. It's just that, like, I think I might have to cut this stream short. A good thing, though, I'm cutting it short, because I hit a pretty big roadblock. I think I need to redo my algorithm. I think. Chat says, does tracing overhead not negate the perf? Well, the tracing happens when you're in an interpreter, so it's in an interpreter loop. So you already have the huge overhead of interpreting, so there's a minimal overhead of doing the tracing. Also in generated code, tracing could be as simple as incrementing an integer, right? You want to find hot code. You want to find how many times this loop ran. Okay, at the bottom of the loop, we increment an integer. There's two ways that's like the simplest way to do tracing, and I think that's how most JITs do it. They just have an integer that they increment at the bottom of a loop. They say, okay, this code is being run a million times. Vic says, good, shows you're passionate. Thanks. I'm pretty passionate about this. But I think that's where I end the stream. I think because I think because this gets really hard when it comes to variables. I think it gets super hard when it comes to variables. I think I'm done here. If you guys have any more questions, be happy to ask, but I think I'll make a commit. Zakazaki says, what's the issue with the algorithm? Okay, I'll explain. I think I already I glossed over it a bit. Okay, so this here all says all arguments to a terminator are roots, but this is like a step 0. Start at all. Yeah, step 0. Start all red instructions. Okay, so let's just assume we're starting at the bottom of a program. All right. So we're checking all of this here, and then we're reading a value of f. But we don't know the value of f. We have to go all the way up to the top, and then check it. That's one of the big issues. And you know what? There's this thing with all uses dominate defs, and I think I wrote this down here. Since all defs dominate uses, I think I could do 2 passes. Okay, here I can do one. So let's say I'm inside this block. I'm checking it. I'm going bottom up, checking all the roots. You see F, right? F doesn't have a type. You can't do this, right? You have to go when you reach something. You have to know its type. So you'd have to parse up here first. You'd have to go up here first, but then you'd lose the type information when you're parsing it up. I think my suggestion. What I'm planning to do is, 1, ascertain the type of all user variables. Then ascertain the type of all SSA variables, and that requires going into rets and following these steps. Okay, so the whole point of going bottom up is so I can use the information of the return value, because let's say this is a function and I'm returning a tuple here, and I'm like saying, okay, so that means 0, that means 12 is supposed to be U8, because it's like inferring. This is bidirectional type inference. It's going up. So I need to bring the type information upwards into here, and that means %2 is a UA and stuff like that. But the thing is like, no information can't flow into the use of a... No type information can't flow into the use of F here. So this I32 is being put to here. You can't flow type information into an F. That means like this is nonsensical. So it like there's no point. but there's another thing, like all defs dominate uses, which means you could start all the way up here and then go all the way back down here. But it makes sense to do it in two passes. So first, I ascertain the type of all user variables. So I go here, f. Okay, so I can ascertain the type of f now because it's being assigned. And then I have all the variables that can be used multiple times. And then now I just ascertain the type of all SSA variables going down. But this also comes to an issue of, let's say %11 equals 20, and then I'm using it here, because you can still use SSA variables up here irrespective of control flow. Okay, so this algorithm is dumb. This algorithm is dumb. Flood fill with recurse upwards. Recurse. I think I need some complex algorithm. I think I need some kind of, I don't know. I think I need some kind of like, some kind of graph traversal. It's super complex. I'm trying to wrap my head around it. It's something I can't solve on stream. I'm gonna have to solve it on my own. And I've been trying to solve it all day, by the way. Keep that in mind. I've been trying to solve this all day. I think I'll be fine. I think yeah, I think I got mostly there. Anyway, if anyone has any more questions, I can answer them. But I think I'm gonna end stream. I think that's it. Type checking. Type check on AST feels much simpler. It is. It is much simpler. Compared to reverse order, yeah, you're right. It is much simpler. But we lose out. I don't want to generate. We lose out on like I don't want another parsing. I don't want another step in my compiler that lowers it. You know, if we can just do this algorithm right here, we're done. And it seems really trivial in my head. It seems really trivial in my head. We have type information flowing up and type information flowing down. It could be as simple as two passes. One pass going up, assigning all the types where it's needed, and one pass going down. It seems as simple as that, but I'll have to do more tests, right? Thought experiments. I'll have to do more of that. But there is an advantage. There's a reason why I chose this SSA unwrapped thingy. But I think that's it. I think I'm done. I think I'm done stream. So I'm gonna end the stream in 10 seconds. So if anyone has anything to say in those 10 seconds. 10. No, I'm not gonna count. Yeah, I think I'll perform the commit. Say goodbye to everyone when this is done. Hold on. I'm gonna check. What stream is this? Stream 12, right? Stream 12. Wow, come a long way. Stream 12. Implement scaffold. I think that's right. All right. Thanks for showing up. I really appreciate it. Thanks for letting me talk and everything. All right. Goodbye. See ya. Thanks guys.